Here's the solution to the warm-up problem. This was on that little quiz at the beginning, the form. If you haven't done that, pause and go take care of it now. I love to put these kind of questions on quizzes and tests, so you'll definitely be seeing some of these on assessments. And make sure you're able to handle these type of domain questions as it relates to making formulas and doing them from a shape, something in real life. So we've got this area to fence in. It's a rectangle, so these two sides are the same, these two sides are the same, here's their dimensions. And I've given you the formula, I've already made it for you. The area in terms of x, so the output area that you're going to get in terms of the input x, which is determined by this side, is 100x, 100 minus x times x, so that's our formula. So it's kind of like the volume problem we did on the last set of notes. The area also must be bigger than 0. If you have an area of nothing, you don't have a plane, you don't have a space, you have a single point again. So our area, in order to exist, has to be positive. It has to be bigger than 0. So I'm just going to go ahead and kind of put that in there as a little side note. Area has to be bigger than 0. So that means that if area is bigger than 0, and this stuff is my area, then the 100 minus x times x has to be bigger than 0. And again, by fundamental theorem of algebra, take each one of these, make it its own inequality. And this one's done, nothing more we can do with it. And to wrap this one up, 100 is greater than x. So I told you how to do this with an and statement last time. I'm going to show you one more way to do this, or at least another way to write it. So you could say x is greater than 0 and x is less than 100. Another thing that's kind of a shortcut is to put x in the middle and just make sure that the point's going toward the same thing it was. I kind of switched that around with the big end's facing x, little end's facing 0. As long as I do that here, I'm good to go. Same deal, I kind of switched that one around as well. But this is a good way to show it. Your domain is anything from 0 to 100. It doesn't include 0 or 100. It's kind of like the volume problem we did in the last example. If this length x becomes nothing, then the area I'm fencing in has no, it's just a line of fence, doesn't enclose any area. And if the bottom side is 100 feet minus x, well then if I've used up all my length this way, now I no longer have any width this way. So same deal, that's why I've got those constraints. And I put it in Desmos just so you can see how it would look on a graph. So from 0 to 100, that's my domain. And we won't do too much of this in pre-calc without a calculator. Or actually, well, we'll do a little bit without a calculator, but not too much. You can actually use calculus. One of the biggest things calculus helps you do is find these maximizations, which if you want to, I didn't ask you to warm up, but if you want to figure out the dimensions that give you the most area, maximizing that function's how you do it. All right, now let's take a look at the actual lesson. So lesson 1.3 in your book, it's going to be called Graphs of Functions. The first type I want to look at is piecewise. And I know we've looked at it a little bit in the first section, so now I'm going to give you a little bit more detail and really focus now on how to make the entire graph instead of just plugging in a single point. So let's take a look at how that's going to go down. We do still have these domain restrictions. We have one piece of the graph that's going to be from 2 and to the left. We have another piece that's going to be from 2 and to the right. And neither one of these are exactly equal to 2, so you'll never actually have a point right at 2. And I'll explain that a little more when I talk about the final domain. So 2x plus 3 is the equation when x is less than 2. What I always like to do is just graph these lines as if you're going to graph the whole thing. Don't worry about the domain restriction yet. But I like to just get points. Don't draw the line in dark yet, just kind of lightly do everything. So 2x plus 3, intercept at 3, and slope of 2. All right, and if you can kind of think ahead, I know I'm going to stop at 2, but I could keep going, and that would be fine. But then when I look at my domain restriction, all right, it's from 2 and left, so I need to start here and go this way. And then I need to look at this part too. It's not equal to 2, so I also need to make sure I've got an open circle going on right at 2, when x is 2. The other part is a constant, 5. So your y value is always 5, no matter what, no exceptions. And I just realized I'm going to erase the rest of that line if I made anything else out there. So y is always going to be 5 no matter what. So what I'll do is just kind of make a little dotted line along there. There's my constant function, y equals 5. I don't want to draw it in real dark yet. I would just do this real lightly with a pencil if I was doing it on paper. This is only going to be true if x is bigger than 2. So starting at 2, but with an open circle because it's not equal to, and then going to the right. That's going to be the rest of that line. So then I come back and erase any other points that I've made that aren't really part of my graph. And that would do it. That's your piecewise. So in Algebra 2, hopefully this kind of rings a bell, you would see graphs like this and have to come up with the domain from them. So that's why I kind of want to wait till this part. But you've already been given the domain. X is less than 2, or x is greater than 2, but neither is nothing right at 2. Because if I plug in 2 for x, there's open circles there. There's never a y value that it gets mapped to. The next example is to look at intervals of increasing and decreasing. This is always in terms of domain. And when we look at the graph, I'll come back to this again, but it's kind of tempting to think of it in terms of range because of the way the graph's going up and down. But it's always about domain. It's always about the x values. I mean, I'm going uphill from this x to this, or I'm going downhill from this x to this other x. I'm going to keep focusing on that because that's a really easy place to mess up, but a really key thing we got to focus on. So here's my function, and I went ahead and put it in Desmos. I kind of mentioned this earlier. Calculus gives us a really nice way to get these kind of peaks and valleys, kind of tell us where it maximizes, minimizes. Calculus gives us a really good way to do that, but we're not there yet. So we're going to keep using the calculator, and that's going to hopefully make this a little bit easier for you. So here's what it would look like as a graph. It's got a local maximum and a local minimum here and here. If you need help with the calculator, figure that out. I'm pretty sure you've hopefully done enough of that in the background to know how to find your maximums and minimums. But let me know if you need help with the calculator. I can put something out there to show you that part. Also, I said local max and min. Well, local means if you got to cut the ends of the graph off and just look at the kind of useful part in the middle, because this is a local maximum, but the absolute maximum, this thing goes up forever, so it'd be infinity. But if I was trying to model some data and match this to it, I probably don't care about what happens as time goes on to infinity. I probably care about what happens in the next few years or something like that. So if we look at the middle part of the graph, we've got a local maximum at negative 0.155 and a y value of 1.079. What I care about is the x values that's happening at. So when I make the domain here in a second, it's from negative 0.155 to 2.155. Okay, that's where this thing is, that's the domain where this part's going on. So I'm increasing, I'm going uphill from eternity past, so negative infinity, up until negative 0.155 for an x value. Again, it's all about the domain. I usually like to think about mile markers. When you go down the interstate, you don't usually see elevation markers. The interstate goes up and down, especially here in the valley. But you see mile markers. You see markers horizontally where you are down the road. They don't mark it by how high up in the air you are. So that's a good analogy that usually helps students kind of keep this straight. It's about the mile markers. It's about going horizontal, not about how high up you are. So again, increasing from negative infinity up to negative 0.155, and then decreasing from the negative 0.155 to 2.155, and then down at positive 2.155 to infinity, we are increasing. Okay, so let's put those kind of formally, see if we got the idea. So we're increasing from negative infinity to negative 0.155. Okay. And I'm using that notation again that I showed you on the warm-up. It's just a lot easier to show it that way. When x values are between negative infinity and negative 0.0155, then I am increasing. Okay. Now, I was decreasing from the 1.155 until I got to, I'm going to flash back real quick to see what it was, 2.155. And then I was increasing again from the 2.155 onward to infinity. This is usually how you're going to see this done. This is kind of the, not necessarily the only notation, but the usual notation you see for intervals of increasing and decreasing. Okay? Now, constant. This is sort of a question that usually comes up in the lesson in class, so let's talk about that. When I explain this in Algebra 2, I always kind of think about driving along and it's foggy and you think about your headlights and what they're doing. Well, if we're increasing, going left to right, if we're increasing, our headlights are going to be going up in the air. Okay? If we're decreasing, our headlights are going to go down, going down. So I always like to talk about what happens when we top that hill. At some point, my headlights would be shining straight out, horizontal, not going up, not going down. The thing is, it's sort of an instantaneous little point here. We could identify that right at that particular point, we're constant because we're not going up or down. But we usually don't put that in there as a constant. Usually constant is when you have an actual distance that you can measure that's horizontal. That's what we're talking about when we have a constant.